Hello, calculus students. This is Mr. Beck, and today we're going to be talking about the latest in the set of rules for calculus derivatives. Just as a quick recap, in 2.1 we learned the definition of derivative, and we took the limit definition and we explored that. We explored that with the power rule, and we learned that in 2.2, where we said, okay, why does the power rule work? And the power rule works because of the binomial theorem. We talked a little bit about that. Then in 2.3, we explored what happens if we have a product and we have a quotient. Products and quotients are functions themselves. So one of the things that we're looking at is if you have a function, how does a function change? That's really what a derivative represents, how a function changes. So the product of two functions is itself a function, and so we learned how it changed, v du plus u dv. And quotient rule, we learned how that changed, v du minus u dv over v squared. So today we're going to be talking about, as I said, the latest rule, which is the chain rule. And what kind of prompts this thought is, what happens if I have a function f of x equals, let's say it is 4x squared to the third power. So the question is, does the power rule apply here? So that big question, does the power rule apply? So if it did apply, f prime of x would be 3 times 4x squared. So which if we simplify it, and by the way, I'm going to put a question mark here just to say, does this actually work? And if we distributed, we'd have 4 squared root to 16. 16 times 3 is 48. So that's 48x to the fourth. So the question is this the true derivative? Going along with that, well, let's go ahead and multiply this out right from the beginning. F of x is 64x to the sixth power. And f prime of x really should be 6 times 64, x to the fifth. Now, I don't know what that is off the top of my head, but I can tell you that that is not exactly true. Those two are not the same. Therefore, the power rule should not be able to apply. So I'm going to say no, no, no. Except when I start exploring that a little bit more, if I realize that if I multiply this by, let's just say, a random 8x, then yes, it is equivalent to that number. I know you probably can't see that immediately, but it's true. And the question is, where does this random 8x come from? It's not quite so random at all. In fact, it's the derivative of what's inside. And that leads to, let's start off with the overall general power rule, that if we have some function to the nth power, then the derivative is n f of x to n minus 1 times f prime of x. So the way that I look at this is, how many functions do I have? I have 2 functions here. And each function has to be represented by its derivative. The outermost function is our power, so that's why we see the power function derivative applied right there. And then the inner function is, I'm just going to call it inner function because I don't know what type of function it is, but the inner function then is the derivative, or the inner function's derivative shows up at the end, and that's what we call the chain. We see that a little bit better notationally if we look at this, that f prime of g of x, so we take the derivative of the outer, so the derivative of the outer function, times the derivative of the inner function. And I like to joke about this sometimes as doubt or dinner. So take the derivative of the outer times the derivative of the inner. So as I'm looking at this expression, what I showed in class was, if I want to take the derivative of 2x plus 3 to the second power, the very first thing I do is I identify what is the inner function, what is the outer function. So in blue, I have here the outer function. In green, I have the inner function. So the way that our chain rule applies is we take the derivative of the outer function. This is what the power rule does. Drop the exponent, take whatever's inside to the first power. So this is the power rule. And then times the derivative of the inner function. The inner function is a polynomial, linear. And the derivative of that linear function is just 2. Put it all together, and let's go ahead and clean it up. 2x plus 3, let's put that back in there. And then we clean it up in this step. And like always, please try to factor all of your results as much as possible. For part B, let me go ahead and do the highlighting. So the highlighting is, this is our outer function. So we start by taking the derivative of the outer function, which is what you're seeing there, followed by the derivative of the inner function. The derivative of 3x to the fourth minus 2x minus 1 is 12x to the minus 2. And then we go ahead and clean it up. When we clean it up, anytime that we have, let me change colors, anytime that we have a denominator, we want to make sure that that shows up in the denominator. Negative exponents, we really do not want to see those negative exponents. Therefore, how do we apply negative exponents? We put that in the denominator as well. For our third problem, once again, we have two functions occurring here, our outer function and our inner function. And our outer function is going to be the exponential function. So our outer function is e to the x. And if you remember, what's the derivative of e to the x? The derivative of e to the x is itself, which is what we see here. So our outermost function is that e function. And then, don't forget, times the chain, the derivative of that inner function is x minus 2. There's not really a whole lot of simplification that we could do here. I personally would leave this as an answer. I would accept that as an answer. This is better. This is better because that 2 is factored out. So what I was saying is, personally, I would not count off if you didn't factor a scalar multiple out. Scalar multiples don't really affect the derivative as much. And why do I want to factor? I mean, that comes back to, why do I care about factoring? Factoring tells us where our derivative equals 0 and where our derivative is meaning horizontal tangents, and where our derivative is undefined. And why do we care about those specifically? That's where our derivative changes signs, and I'll wait until we get into the applications of that in chapter 3 before I go further. Right now we're setting up those essential skills of, hey, can you take the derivative, and then can you factor all of your results? So, part D, this is our first sense of trig. Trig, our derivative, we have sine, so we have the sine function, and we have 3x as a function. So our outermost function is sine, our innermost function is that linear 3x. Our derivative of sine is cosine, and then the chain of that 3x is 3. And again, there's not a whole lot of simplification that we could do on that. E. So when we look at E, what you can see is I broke this up into 2 different parts, meaning 2 different terms. And the thing that I need to highlight is that multiplication ends up being the dominant factor, or really the dominant function right now. We have 2 functions which are multiplied by each other. And in order for us to take the derivative, that product rule must apply. So that product rule is v du plus u dv. Now don't forget that there is a chain involved right here. So the derivative of negative x is -1. And then simplify and factor as appropriate. For f, this is our first opportunity where we're not seeing just 2 functions, we are seeing 3 functions. Our 3 functions, our outermost function is going to be that polynomial, or sorry, that power of 2. The innermost function is 3x. So if you notice that there is a middle function that's occurring, that middle function is sine. It's a lot easier to see it in this form right here than it is in the original form. So like before, let's start by taking the derivative of the outer function first, and we can apply that power rule like so. Then we take the derivative from the outermost to the innermost. So now we take the derivative of the sine, which is cosine, followed by the innermost, the derivative of the 3x is 3. And then simplify the result. Now, both of these are acceptable answers. This one is a much cooler answer just because it uses the double angle formula for sine. Moving on to G, which is right here. So our G right here. Anytime we have a bunch of radicals, it ends up looking nasty, which is why I strongly encourage you to please take all of your radicals to the exponential form. So the derivative of the outermost function is the power function, and I have that as the wrong color, so let me change that. So our outermost function is this power function, and then we have our inner function. This is really just a combination of 2 different parts. Derivative of the outer times derivative of the inner, and there's not really a whole lot of explanation I need to do here anymore. Yes, it's some ugly number or ugly fractions, and part of me apologizes for the ugly fractions, but at the same time, working with the ugly fractions helps you understand and appreciate those numbers a little bit more. H, once again, the predominant function that's occurring here is the multiplication that's going on. So product rule occurs, v du plus u dv. And don't forget, when you're taking the derivative of v, that we have, in this case, it's 1/2 what's inside to the -1/2, and then the derivative of the inside is that -2x. Now, I have two terms here, and this occurs quite a bit, but I have two terms here. And these two terms, what I do is I look for what is common between both of these terms. What's common between both these terms? I see that I have an x, and I see that I have the 16 minus x squared to a power. So we take out the smallest power out of each one of those, and I like to show that I'm going to be taking both of those out of these two terms. Therefore, I like to put the brackets there. It's really just how I format it. And then next step, clean up, followed by write your result as one fraction. So again, general order of how I do things. We apply the product rule, or if we have the quotient rule, we apply that too, just because those rules apply first. And then to take the derivative of the functions, so VDU plus UDV, clean up, factor, sorry, I guess it's clean up, factor, and then clean up that result until you get to an answer. I. So on I just applied, there is a product rule occurring right there. So I just applied the product rule. And I will say, I'm very unhappy with this result because there's not a whole lot that I can do with it. I didn't even bother taking it any further just because you're just rewriting the order of the terms, if anything. Although I take that back. I do see that we have an e to the 4x minus 2 that we can factor out of each one of those. That would be 3 cosine of 3x plus 4 sine of 3x. Still not a whole lot we could do after that, which is okay. So on J is the first opportunity that we see a polynomial times a polynomial. And when we see that polynomial times a polynomial, once again, it's a product. Ooh, that jumped up. It was not supposed to do that. So let me find where we are. There we go. So that product rule that's occurring right there, we end up with two terms. So we have VDU. I guess I wrote this one as UDV, which is okay. UDV plus VDU. So UDV plus VDU. Once again, what's common to both? I see a 2x plus 3 that's common to both, the smallest exponent that we take out. I see a 3x minus 1 common to both, and the smallest one we take out is the power of 2. What's left over is going to be this expression and simplified. Now, I do want to take a moment when I look at this and say, okay, once again, what's the purpose of me factoring all of these? When I factor all of these, what I'm doing is I'm establishing, and I really want to know, where does this equal 0, because that gives me horizontal tangent. If you remember from pre-calculus, if we asked you to graph an expression that looked like this, what we did was we looked at where the zeros were. It looks like the zeros are going to be -3/2 and 1/3. And what ends up happening, I know this is a positive 8th degree polynomial. The positive 8th degree polynomial will end up doing something like this, where we have just like these flat, it comes through flat on the graph. So what this shows is both of those factors that we had in the initial problem show up as the horizontal tangents that are occurring right here. And then this last one, x is -17/48, that's the one that we were not able to find. Let me change colors so we can see it a little bit better. But that x value was what we could not find in pre-calculus. We didn't know exactly where it was, but calculus gives us that opportunity. Example number 2, officially example number 2. Just set it up, make sure that you know how to work with all the fractional exponents. And once you've worked with those, then overall outermost power times the derivative of the inside, and hopefully fairly self-explanatory. On to new functions. The derivative of the natural log function, derivative of natural log is 1/x, which is a very, very happy thing, because the derivative of natural log just being 1/x, it turns what we call a transcendental function into more of a power function or a polynomial function style. So in this case, it would be power function because it's x first. So the derivative of the natural log is 1/x. I don't like just saying, hey, this is your derivative, deal with it. But to show this derivative a little bit more properly, then what we would do is we would use what's called implicit differentiation, which we're going to learn in 2.5. So we're just going to go ahead and say, okay, here's a rule. I hate doing that, but we could do that. Now, most of the time we don't just have an x inside that natural log, we have a function. So the derivative is 1 over what's inside times the derivative of what's inside. A lot of times written as du over u. And one of the reasons why we use the natural log function quite a bit is because in kind of like a business context, this is how we represent relative change. Relative change is the amount of change over the initial. If you look at that derivative of the natural log function, that amount of change is what du represents, and over the initial is what we began with. So natural log has quite a bit of functions if you look at, or quite a lot of purposes if you look at real life applications. Now, there is one other thing that I do want to look at is notice how we have an absolute value. The purpose of the absolute value really expands the domain of what's inside that natural log function. But if you realize it does not change the actual derivative result. The reason why is because when u is a positive function, so when u is positive, then your derivative is 1 over u. When u is negative, what that turns it into is the natural log of negative u. And its derivative would then be negative 1 over negative u, which is also 1 over u. So quick proof to show that just because we have the absolute value function in there doesn't mean that we have to treat it any differently. So with that said, we begin by saying, okay, what is our outermost function? Our outermost function is the natural log function. And how does the natural log function's derivative work? We take 1 over what's inside, so the outermost derivative, times the derivative of what's inside, which is 6x squared. And if you see, that simplifies to 3 over x. One of the reasons why I love logarithms is because once you understand the properties of logarithms, you know how to play with them. You can get to those derivatives a little bit faster. If you notice, that's what I did over here. I first broke the natural log of 2x cubed into natural log of 2 plus 3 natural log of x. And the natural log of 2 is a constant. So since it's a constant, its derivative is going to be 0. And we get to the answer a little bit more simply, but at the end, it really doesn't matter how you get to your derivative, just get to your derivative. So for part B, product rule that occurred, keep in mind that product is huge. So VDU plus UDV, simplify, factor. Here we have 3 functions. Our outermost function, which again I'm going to do in blue, is that 2. Our innermost function is going to be the x plus 5, which means our middle function then is going to be the natural log. So when we take the derivative function by function, power function derivative occurs here. Then how does the logarithmic derivative occur? It's 1 over what's inside. And then the innermost function, the derivative of what's inside. Now, do you really have to write that 1 there? No, you don't. I will tend to write that 1 just to show that I'm always thinking about the chain rule as I do the problem. For part D, this is a situation that if you see, I started doing this 1 over what's inside times the derivative of what's inside, and then I'm like, this just ends up being nasty, and I don't really feel like doing it, especially when we have this alternate approach of let's break our logarithms apart. And then when we break our logarithms apart, our derivatives are much, much simpler. And then, yes, we do have to combine together, but I'll tell you that's a lot less work than what that would have been, so I'm happy. And here is my overall result. For E, let's go ahead and break it into 3 terms. Natural log of x, that multiplication means plus 2 natural log of x squared plus 1, and then minus, because it's in the denominator, 1/2 natural log of 2x cubed minus 1. Now, with all of that said, what ends up happening is we take our derivative, 1 over x, that one's pretty straightforward. 2, I wrote this as just the derivative over what's inside, derivative over what's inside. If you notice, I have here, the moment we have 3 or more terms, I'm kind of okay to leave it. I hate to do that, but at the same time, I'm like, okay, the point is not to do all the complex algebra, even though that's a lot of fun in my opinion. It's to make sure you know how to take the derivatives, and let's go ahead and move forward. Especially with this problem, we could use a calculator to find the derivative, which is why we have the task group. So F, again, we can ignore the absolute values because in the end, they don't actually matter. So we have 1 over what's inside times the derivative of what's inside, which gives us negative tangent of x. And once again, a lot of trig is very related. And this is going to be important when we get to chapter 4. Excuse me. So what happens if we have a base other than e? If we have a base other than e, then what ends up, what our derivative is itself times the natural log of the base. So itself times the natural log of the base. Now, the reason why this is true is because a to the x can be written as e to the natural log of a to the x, which we could use properties x natural log of a. So let's say that equals y. Then dy dx is going to be the derivative, which would be itself times then the chain of the exponent. The natural log of a is a coefficient. And then if I rewrite that as a to the x, then we get the expression that we see right here. So just if you think about it, when we took the derivative of e to the x, there were actually 2 hidden chains here. The first was the natural log of the base, which the natural log of e is 1. Then the second is the derivative of 1, which is the derivative of x. So really, we've been working with chains for quite a while, but we just haven't actually shown those chains because we were learning how to do this function by function. So with that said, the other thing that I want to mention is if we are taking a log with a different base, I personally, yes, this is a rule. I don't need ever think about this as a rule. What I do is I use the change of base formula from pre-calculus. Then I look at 1 over the natural log of a as a coefficient. I kind of cut that off. So as a coefficient times the natural log of x. And then the derivative of natural log of x is 1 over x. And remember, it's all coefficient. Therefore, it is what it is. And then if we have a function rather than just x, then that's where that chain comes into play. So with that said, I look at a, and the predominant feature is this quotient rule. So quotient rule is v du minus u dv over v squared. Then this is going to be my, let's clean it up a little bit, factor it, and then simplify. If you want to say clean it up one more time, I understand that. So for part B, the predominant feature is we have a product rule that occurs. So we have, this is v times du. So v times du plus u times dv. And I like to use that differential notation quite a bit. So then what can we do to clean it up? Pretty much it's just this. Notice how I took that fraction out. I like to always take the fractions out because then, I'm surprised I didn't write this as an answer. We have cosine of 2x times natural log of 5 plus 8 sine of 2x all over negative 4 times 5 to the x over 4. We can turn that negative exponent into a positive exponent. So here's my answer. All right, for C, outermost function is our tangent function, so derivative of tangent secant squared. And then we say, what's the derivative of 2 to the negative 3x itself times the natural log of base times the derivative of the exponent. And then that's just the simplified version of it. If you can call that simplified, it's not really much. For D, this is where I said, okay, remember, I don't ever think about this as a rule as much as let's go ahead and apply logarithmic properties. Change of base, 1 over the natural log of 2 times the natural log of this expression. I just went ahead and broke it apart using log properties. So whenever now I'm taking my derivative, by taking the derivative, the scalar multiple does not change. Derivative of 2 natural log of x, and we have the derivative of natural log of x minus 1. Combine and simplify into that expression. Same thing here. Change of base formula, turned it into that. Simplified, derivative, and with our derivative, our scalar, there was a 1 in the numerator here, if you will. So we have a scalar and then times the derivative natural log of x squared minus 1, which is 1 over x squared minus 1 times the chain 2x, and then simplified result, followed by f, which once again, using the change of base, I rewrote it in this form. So, and that's because this is the natural log of x over the natural log of 4. I just rewrote it in a form that made it look a little bit more like a, I don't want to say power rule, but this is our scalar times what are the functions doing. Hey, there's a quotient. That's very, very important. Let me get rid of that. So quotient, so we have v du, that's times, minus u dv, which is 1 over x squared, and simplified result. So I do have a couple of AP style problems that are not in your homework, but I have them on these notes. So I'll go ahead and show them, and my work hopefully is self-explanatory enough that you're able to understand what those answers are and why those answers are what they are. So I will leave you with that. Calc students, I hope you have an amazing Labor Day weekend. Bye.